Is titled Circular Motion Part 2. So this is more or less a continuation of the previous lesson, where I'll be getting into a bit more detail in terms of the quantitative and qualitative aspects of circular motion. So just to recap, so what is circular motion? Circular motion, if you recall, involves an object moving in a circle, object of mass m, at constant speed and is constantly changing direction. Okay, and hence velocity, changing velocity. And its velocity, also known as its linear velocity, or tangential velocity, is perpendicular, so V is perpendicular to the centripetal force, F sub c. Okay, and the dot here is the center of the circle. And the most typical example is that of an object being swung around on a rope, where the centripetal force is provided by the tension of the rope. And if I was to draw sort of a snapshot of the object moving along at different points in time, let's say I've got an arc here, part of the circle. I've got the object of mass m. Let's suppose it's moving towards the right. Its velocity will be like this, okay, in a straight line, perpendicular to the centripetal force. I'll draw a right angle here to emphasize. Let's suppose at some other instant in time, it's now here. Now the velocity would look like this, centripetal force like this. And this is obviously not to scale, and it's been exaggerated, so it's not probably accurate, but it's just a good visual way of visualizing what's happening. And here, in this case, it's a flat line, the tangential velocity, and the centripetal force will be going downwards like this. And what you can probably notice is that the centripetal force is being directed towards the center of the circle, more or less. And it's also worth noting from before as well that the changing velocity of the mass, changing velocity, implies that there's also that the object is changing direction, which also implies in turn that the object is accelerating. There's acceleration. And acceleration is given the symbol A sub c, and the c stands for centripetal acceleration. So an object in circular motion will also experience centripetal acceleration, apart from a centripetal force as well. And just like the centripetal force, the centripetal acceleration is always directed towards the center of the circle. And it's also perpendicular to the velocity too. So note, so centripetal force is perpendicular to the linear velocity, and the centripetal acceleration is perpendicular to linear velocity. And mathematically, you recall the centripetal force is just the mass of the object times its velocity squared divided by the radius of the circle, r for radius. And the centripetal acceleration is just the velocity squared of the object divided by the radius of the circle, where centripetal force has units of newtons, radius of meters, velocity of meters per second, and mass kilograms. So the typical SI units we use in physics. And just to note, the centripetal force is directly proportional to the mass of the object and its velocity squared, and inversely proportional to the radius of the circle. So note, centripetal force is directly proportional to the mass of the object, the velocity squared of the object, and is inversely proportional to the radius of the circle. And similarly, the centripetal acceleration is directly proportional to the velocity squared of the object and inversely proportional to the radius of the circle, of circular motion. So in other words, doubling the mass doubles the centripetal force, okay, whilst the velocity and radius are kept constant. doubling the speed of the object, the velocity, doubles the force as well, while keeping the mass and the radius constant, and so on and so forth. And in terms of radius, if you double the radius, you half the force. And if you half the radius, you double the force. Okay, it's just simple stuff from algebra. So let's now see how we can rewrite the centripetal force equation in terms of other quantities that we've come across before, particularly in prelim physics. So we'll start with the definition. So let's define the period t. It's given the unit, the symbol t. So period from your waves and thermodynamics module in year 11 physics is the time it takes for an object to make one complete revolution, one complete cycle, in other words. And in the case of circular motion, the distance d completed during one cycle, or one revolution, is just the circumference of the circle, which is just 2 pi r from basic maths, yeah? So therefore, the average speed of the object in terms of the circumference of the circle is just 2 pi r divided by the period t. And why is that? Because remember, speed is just distance divided by time, d divided by t. Distance is 2 pi r in this case, and the time, we've just replaced it with the period. Okay, and this has units of meters per second. Okay, because r is in meters, period t is measured in seconds, so it's meters per second. Let's have another definition here. Okay, angular velocity. Now it's the same thing as normal, ordinary linear velocity that we're all familiar with every day, okay, moving back and forth, let's say. But angular velocity involves circular motion. So it's velocity in terms of circular motion. So angular velocity tells us how the angle changes every second. Okay, your angle, the angle that you're moving with in the circle. It's given the symbol omega. Omega is a curly W, it's a Greek symbol. Now there are 2 pi radians covered in each complete revolution. Okay, 2 pi is just equal to 360, in other words, 360 degrees. Radians is another way of measuring angles, right? In maths and physics, 2 pi radians. Okay, taking r to be 1, let's say, for a unit circle. Okay, so 2 pi r becomes just 2 pi, looking at a unit circle. And so therefore, omega, we can express the angular velocity in terms of 2 pi and the period. Okay, same thing as before, because velocity is just distance divided by time. V in this case is the angular velocity, which replaces with the angular velocity, omega. This distance is 2 pi, and the period t is just the time, right? And that is also equivalent to, so these 3 straight horizontal lines means equivalent to, is equivalent to, mathematically, 2 pi f, because if you recall back from waves and thermodynamics, the frequency is just the inverse of the period. F is equal to 1 over t. It's a property of waves. We can also express the angular velocity in terms of the linear velocity and the radius of the circle. It's just the radius, the linear velocity divided by the radius, because as from before, the definition of angular velocity, it's velocity but in a circle, right? So it's moving, the velocity is moving through some radius r. And so therefore, we can express the linear velocity in terms of omega and r. And using this fact, we can re-express the centripetal force m. Now, Instead of v squared, we're going to replace it with omega r all squared. Okay, because that's what v is equal to, divided by r. And that is just m omega squared r squared divided by r, which is just simplifying m omega squared r. So this is the centripetal force in terms of the angular velocity. Let's do an example. So let's suppose we've got a 100 kilo mass moving in a circle of radius 1 meter, completing 10 revolutions in 1 second. We need to work out the period, frequency, and centripetal force of the object. So let's do this one step at a time. Now, we're going to work out the frequency first, rather than the period, because frequency is just 1 divided by period, right? And we know what the period is. In this case, it's just 1 second. Apologies for that. Frequency is a measure of how many revolutions occur per second, right? So it completes 10 revolutions every 1 second. And that is just 10 revolutions per second. So that's the frequency. We can now use this to work out the period, because the period is just 1 divided by the frequency, the reciprocal of the frequency, in other words. And that is just equal to 1 divided by 10, as we've calculated, which is just 0.1 seconds. So having calculated these two quantities, the frequency and the period, we can now work out the centripetal force. mv squared over r. So we know what m is. M is just 100 kilos. However, v needs to be expressed in terms of circular motion, which is just, so the quantities in terms for circular motion, that's just 2 pi r divided by the period. Okay, rather than just having v by itself. We know what this is, so it's just 2 pi times r. R is the radius. That's just 1 meter times 1 divided by t, the period, which is what we've calculated here before, 0.1. Calculating that gives us, it's about 62.83 meters per second. I put 2 decimal places just to make it more accurate. And so we can plug this into v, expression for v, and that's just equal to, so back to mass. Mass is 100 kilos. 100 times 62.83 squared divided by the radius 1. And calculating that gives us a massive number, 394,760.89. So 394,760.89 newtons, a massive force.